Hi everyone, my name's Georgina and I'm a PhD student from the University of Adelaide, and today I'll be talking about descending into the snowball, improving interpretations of Tonian palaeoenvironments with multi-proxy elemental and isotopic geochemistry. The Neoproterozoic era from around 1000 to 541 MA represents a period of significant physiochemical change in Earth's history. This includes variations in oceanic and atmospheric oxygenation, major biological evolution, tectonic reorganisation, and an extreme icehouse referred to as snowball Earth. Three periods comprise the Neoproterozoic: the Tonian, Cryogenian, and Ediacaran, as seen on the column on the left. The transition from the Tonian to Cryogenian marks the onset of the Sturtian glaciation, which is highlighted in blue. These Sturtian glacial deposits have been recorded on almost every continent, as highlighted by the yellow and red dots on the figure on the right. There's been a lot of recent sedimentological and geochemical analyses from other notable sections, which further warrants the need for a study in South Australia. South Australia has some of the most well-exposed, continuous and thick sections globally, with up to 5 kilometres of glaciogenic sediments alone. Although this is geologically significant, it remains enigmatic as it hasn't been studied in its entirety. There's been few recent studies, and most of those have been focused on specific formations. Within those studies, there's still opposing interpretations of palaeoenvironments, and this highlights the lack of complete contemporary Tonian to Cryogenian research in South Australia. This study is a high-resolution sedimentological and geochemical study. From a SEDS perspective, we'll be looking at the facies and sequence stratigraphic analyses and the elemental and isotopic geochemistry from carbonate samples, which will help us piece together the sequential changes in depositional setting before, during, and after the Sturtian glaciation. This study is located in the Adelaide Rift Complex, which is a 600-kilometre north-south trending basin as part of the larger Adelaide Superbasin. Our field location is located 2 kilometres southwest of Copley Township in the Northern Flinders Ranges. It's made up of 5 formations. In the pre-glacial, the Copley Quartzite, Skilligalee Dolomite and Myrtle Springs Formation, which was represented by the purple. The Bullabalina Tillite represents the Synglacial in the dark green, and the Tapley Hill Formation in the light green is our post-glacial. Just as a quick overview of the facies analysis, we measured an over 3,000 metre vertical section at 1 metre resolution. From this, we identified 17 lithofacies, 9 facies associations, and 16 different depositional sub-environments. The Copley Quartzite was interpreted as a deltaic setting and made up of tabular cross-stratified sands in the lower delta plane, rippled sandstones with syneresis cracks in the proximal delta front, and then at the distal delta front, we had the finer material comprised of these deformed laminated silts. Moving up to the Skilligalee Dolomite, we interpreted a carbonate platform setting. Here, we had intraclastic magnesite forming in ephemeral lakes, through into columnar strandolites, which were deposited in a shallow intertidal to subtidal zone, and then through into massive silts and wavy dolomicrites in a deeper subtidal zone. This same setting was interpreted for the Myrtle Springs Formation, but we see more clastic input, where we see hummocky and swaly cross-stratified silts, more laminated silts, and then still our domal stromatolites. The Bullabalina was interpreted as a glacial-marine setting. Here we had pebbly and boulder diamictites in the subglacial zone, through into finely laminated silts with soft sediment deformation flame structures in the proximal proglacial setting, and then into finely laminated silts in the distal proglacial setting, which had these large drop stones, which were likely carried there by ice rafter debris. Up into the Tapley Hill Formation, we have the same carbonate platform setting. In terms of the lithology, it was a lot more simplistic, where we're depositing massive and laminated carbonates and silts, likely in a deeper subtidal area. This is an overview of our sequence stratigraphy. Here we have our simplified log on the left, our key facies associations. These lighter triangles represent regressive systems, and the darker grey represent transgressive systems. We have here in the dotted lines our different sequence boundaries, which coincide with changes in relative sea level. So looking at our elemental geochemistry, we analysed 42 carbonate samples from the Skilligalee, which you can see here in the pink, the Myrtle Springs in the purple, and the Tapley Hill in the green. We measured these for major and trace elemental geochemistry. We screened them for diagenetic and contaminant indicators, and then from that we analysed the redox proxies. Firstly, we wanted to look at indicators for diagenesis. So the plot on the right shows the manganese strontium, which is used to identify secondary alteration from meteoric fluids. I've overlaid this image with our sequence stratigraphy. Like before, the light grey boxes represent regressive systems and the dark grey transgressive systems. If we look here on the plot, these values with the largest manganese strontium, which again could represent the largest degree of alteration, they coincide with maximum regressive surfaces and parasequence boundaries. This is expected because during times of sea level low, we're more likely to see interaction with meteoric waters. When looking at contribution from shale phases, we looked at zirconium and aluminium and identified just a handful of samples that had high concentrations, so they were excluded from analysis on primary setting. These are the different parameters that we used within our study. We have the cerium on the left, which is used as a proxy for oxia, europium anomaly, which was used to identify hydrothermal input or feldspar weathering, and neodymium euterbium and yttrium holmium are both used as a proxy for the setting. So whether you have more of a seawater open marine signature or a restricted riverine signature. Again, this has been overlaid by our sequence stratigraphy. So if we have a look at this transgressive systems tract in the Skilligally dolomite, what we see is both neodymium euterbium and yttrium holmium are moving towards more of an open seawater signature. Our europium anomaly is quite variable, which could indicate signs for hydrothermal input or feldspar weathering. Our cerium is very consistent. It's sitting just below 1 in potentially a dysoxic setting. Comparing this to the regressive systems tract at the top of the metal springs, we see the opposite. Neodymium euterbium and yttrium holmium are both moving towards a more restricted riverine signature. The europium anomaly is slightly more stable, so potentially less hydrothermal input and or feldspar weathering. And the cerium is just slightly more oxic. If we want to compare this back to our carbonate platform setting, as I said, the Skilligally represents this nearshore restricted environment with dysoxic water column, which would likely be in this sort of zone where you're being fed by both oxic shallow waters and more anoxic deep waters. The Myrtle Springs, on the other hand, could be slightly more cut off from the open system. So we're getting less anoxic deep waters, which is producing a slightly more oxic signature. In terms of the europium anomaly, our Skilligally values are quite high, so we could have large input from feldspar weathering. Next, we want to look at the isotopic analyses. On the left-hand side, we have delta 13C, in the middle, radiogenic strontium, and on the right, stable strontium. Again, they have been overlaid by sequence stratigraphy. If we look at this transgressive system in the Skilligally, apart from these two anomalous values, our delta 13C is quite heavy, which makes sense because that represents carbonate burial, which you'd expect in a transgressive system. We do have quite high radiogenic strontium, which could be because we have a large riverine input. Again, comparing that to the regressive system, we see a slightly lighter delta 13C, which could indicate more carbonate weathering, again, as you'd expect if the sea level was lower. And we have slightly lower radiogenic strontium, so potentially less riverine input. Next, we can plot radiogenic and stable strontium. On the vertical axis, we have radiogenic strontium, which shows a mixing line between our sources. So we have material sourced from enriched crustal rocks compared to depleted mantle. And then on the horizontal axis, we have our stable strontium, which is a fractionation line between carbonates and seawater. As we know, carbonates will preferentially take up the lighter isotope. So they're plotting with a lighter stable strontium relative to the seawater that they are precipitating in. There's some researchers over in the US who are also looking at the stable strontium values for Tonian carbonates. And these are their values here in the green. The radiogenic strontium value is very close to what we know of seawater at the time, which is around 0.7065. And the stable strontium value is quite heavy. It's quite similar to what we see for modern seawater. Comparing that to our data is a lot more radiogenic. We're likely having a lot more stronger riverine or continental input because potentially we're in more of a restricted nearshore setting. And our stable strontium is a lot lighter, a lot closer to what we see from modern carbonates. What could be happening is that our samples could be reflective of a lagoonal system. A modern analogue of this is the Coorong Lagoon, which is a lagoonal system in southeastern South Australia and is primarily precipitating both dolomite and magnesite. This makes sense for our system because not only are we in potentially a lagoonal system, but our carbonates are also dolomites and magnesites, as opposed to this study, which had limestones. So further study for our project is looking at the water chemistry of this brackish Coorong system and also the isotopic signatures of the primary magnesium-rich carbonates that are precipitating there and seeing how it compares to our ancient system. Thank you very much for listening.